All right. Good afternoon. Good morning to everyone. I'd like to welcome you to today's webinar panel discussion on shear walls. My name is Marcy Weaver, and I'll be the education team moderator for today's presentation. Today's webinar is going to run 1 hour, and today's panel and production team, again, Lori Cook, Director of Educational Outreach, and Alita Dean from APA are our speakers. And then myself and Kim Paulson are behind the scenes helping you. Now I'm going to send it over to Lori to get us started.
All right, thanks, Marcy. Let me just get my screen set here. Okay, great. Wonderful. Thank you, everyone, for attending today, our panel discussion on shear walls. As Marcy said, my name is Lori Cook. I'm the Director of Educational Outreach with the American Wood Council. Joining me today is Alita Dean with APA. We're very happy to have her helping us out today. Okay, just a brief disclaimer for this program. It's not intended to provide, it's intended for general information only and does not constitute or substitute for professional or engineering advice. We are recording our webinar today, and by remaining a participant, you would consent to being recorded. If you do not consent, we ask that you disconnect. And we have the copyright, and this program is AIA accredited. Marcy introduced the team today that's going to be presenting. And most of you, I'm assuming, took a look at the course description when you signed up. So there will be a short, the way we're going to have things running today is I'll present for the first portion around 15 or 20 minutes. And then Alita will present for about 15 or 20 minutes, and then we'll do some extended Q&A at the end. As Marcy mentioned, we have a lot of folks present today. We're grateful for each and every one of you, but we probably are not going to be able to get to everyone's questions and our learning objectives as well. We're going to start just with a brief polling question, and I'll let Marcy go ahead and launch that. This one's really easy because there's no wrong answer.
All right, so we have 68% engineers, 23% code officials, 5% architect, 4% builders, manufacturers, or others, and 1% fire service professionals. Thank you so much for all of you being here. We are delighted that you're all here and hope that you find this of value.
Great, that's a good split of folks. Well, thank you everyone again. Okay, so I'll be kicking it off. I'm going to be focusing primarily on the codes and standards side of shear wall design today. So I'm going to start with some references to ASCE 716 and where that references shear walls, and then I'll go into some of our standards here at AWC, primarily the special design provisions for wind and seismic, but we will dip our toe into the wood frame construction manual just for a moment as well. So most of you that are engineers or designers are familiar with ASCE 716, and the latest version has the seismic loads and chapters in chapters 11 through 23. If you go into table 1214-1, that's where it gives you the response modification coefficient for wood structural panel shear walls. And in 14.5.1, it gives you a material-specific reference to the NDS and to SPDWIS, or the Special Design Provisions for Wind and Seismic, for seismic design and detailing requirements. Wind loads are also in ASCE 7. They're in chapters 26 through 31. There are 5 parts of a wood structural panel shear wall. So we have our wood frame, which is typically going to be studs. We've got our wood structural panels, our sheathing. We have nails, which attach the sheathing to the frame. We have plate anchors located at the base of the wall, as well as hold downs at the base of the wall. The plate anchors are going to resist shear, and the hold downs are resisting overturning and uplift. Going into the special design provisions for wind and seismic, we've got 4 chapters in here. And what we're going to talk about today is primarily going to be contained in Chapter 4, which is the lateral force resisting systems. There are 2 types of wood lateral force resisting systems included in this latest version of SPIDWIZ. There's the sheathed wood frame system, which is the traditional wood frame shear wall that I just mentioned that we've all grown to love over the years. And then we have a new system in 2021 that is cross-laminated timber. We're going to focus primarily today on sheathed wood frame shear walls. So we're not really going to touch on CLT other than to provide a couple of references to the sections in the standard where CLT shear walls are discussed. But today's focus is going to be primarily on sheathed wood frame shear walls. So going into Chapter 4, which again is lateral force resisting systems. Chapter 4.1 is general provisions. So this is things that apply to pretty much everything within Chapter 4. 4.2 is diaphragms. 4.3 is where we'll spend a lot of time today in the wood frame sheathed wood frame shear walls section. I'll touch on 4.4 a little bit as well. This is where we have wood structural panels designed to resist combined shear and uplift from wind. And then, as I mentioned, there is 4.6 on CLT shear walls, but we won't be talking about that today in any great depth. So SPIDWIZ has 3 types of shear walls defined within the standard. The first is the individual full height wall segments, or sometimes called the segmented approach. This approach has full height wall segments that have no openings in them, and they have hold downs on each end of these full height segments. So in this illustration here on the left, we see circles, little red circles. Those would be the locations of our hold downs for our full height segments. The other 2 types of shear walls that we have defined in SPIDWIZ do have openings, but there's some slight differences. So force transfer around opening shear walls, or FTAO, are shear walls that have openings, but the framing members, the blocking, and connections around the openings are designed for force transfer. Perforated shear walls also have openings, but they have a reduced shear strength that's used in the design of the shear wall based on the size of the openings. And both of these types of walls would have hold downs present at the ends of the wall, as you can see in this illustration here on the bottom right. So we only have a hold down in the red circles here on the ends of each of these walls. When we go into SPIDWIZ Chapter 4, we have our tabulated shear wall capacity values, and they will need to be adjusted depending on what design methodology we're using. So in the 2021 SPIDWIZ, you may have listened in on our webinar last month where Phil talked about this single nominal unit shear capacity format in the tables. So for seismic designs, for ASD, we would divide the tabulated value by 2.8. For LRFD, we would multiply it by 0.5. For wind designs, we divide the tabulated value by 2.0. And for LRFD wind designs, we multiply the tabulated value by 0.8. So when we go into Chapter 4.3, or I'm sorry, Table 4.3, also in Chapter 4.3, but this is the nominal unit shear capacities for wood frame shear walls. So this is where we've got wood-based panels in Table 4.3a. There are some additional tables for gypsum sheathed walls, as well as lumber sheathed shear walls in Chapter 4. We see that the sheathing material is specified. So wood structural panels, we have struck 1 and sheathing grade specified. The minimum nominal panel thickness is also specified in inches. And the nail type and size is specified, where the length, the shank diameter, and head diameter are all specified prescriptively. To calculate capacities, again, we would adjust dependent upon if we're using a seismic design or a wind design, and if we're using an ASD or an LRFD approach. So for this example, where we've got 15/32 nominal panel thickness with 8 decommon nails at 6 inches on center for our panel edge spacing, our adjusted values would be based off of this tabulated value of 730 pounds per lineal foot. And you can see the adjustments for the seismic and wind, ASD, and LRFD values. I like to point out this footnote in Table 4.3a. There's quite a few footnotes, actually, but this one is one that is new in 2021. So if you have a hold down that is installed on the inside face of the end post, and the unit shear capacity for the shear walls would need to be multiplied by 0.92 if the wall is constructed using 10D common nails. So you can see this illustration here showing that the 0.92 factor is required when we have this inside face of the post attachment for the 10D common nail sizes. But if you're on the outside face, as we see in the bottom right photo here, illustration here, you would not need to apply that 0.92 reduction. It also wouldn't apply for other nail sizes or for rod systems. Perforated shear walls are in SPIDWIS Chapter 4.
Muted.
There was a slight revision to equation 4.3-6 for calculating the shear capacity adjustment factor, the C sub O factor, and accordingly Table 4.356 was updated. So this is the adjustment that is applied to the unit shear capacity based on the percentage of wall openings and the percentage of full height sheathing for that perforated shear wall. Some other items that come up in shear wall design are related to the requirement for 3x framing in section 4.3.7.1, item 5. So where you have the conditions specified here, where you have nail spacing of 2 inches on center, 10D common nails having a penetration of more than 1.5 inches at 3 inches on center or less, or the nominal unit shear capacity on either side of the wall exceeds 980 pounds per lineal foot in seismic design categories D, E, or F, those would trigger this 3x framing requirement. You are permitted to use 2 2x members instead of the 3x member, but it does have to be, they do have to be fastened such that they are designed to transfer the shear between those 2 members. And that's stated in SPIDWIS 4.3.6.1.1. For those of you that use the wood frame construction manual, you'll be familiar with some of the prescriptive design limitations therein. But we do have a shear wall design section in the WFCM in the prescriptive chapter that allows us to design for buildings where our mean roof height is less than 33 feet or 3 stories. And we have some shear wall segment aspect ratio elements that we need to take a look at as well. In general, the WFCM will limit your maximum shear wall aspect ratio for your segments to 2:1. And this has to do with a capacity adjustment that is triggered when we use higher aspect ratio shear walls. The WFCM will allow you to take advantage of those higher aspect ratios, but you do need to adjust the capacity based on the sheathing, or based on the SPIDWIS exception in 43341 for wood structural panel shear walls. So the last thing that I've got just one slide on today is CLT shear walls. And as I mentioned, these are included in SPIDWIS section 4.6, where there's a reference to Appendix B for the design provisions. And we do have provisions for wind and seismic for CLT shear walls. And there is also some additional criteria provided for areas of low seismic hazard as well. So that is all I've got prepared for. So now I'm going to give things over to Alita to talk about her slides, and then we'll get into some Q&A. Alrighty.
Thanks, Lori. So as Lori mentioned earlier, there's 3 different types of shear wall design methods that are detailed in SPIDWIS, and that's that segmented shear wall, the perforated shear wall, and that force transfer shear wall, which we tend to call FTAO, or force transfer around opening walls. I'm going to go through briefly again the differences between the detailing and design for these couple walls, and then I'll show you a tool that you can use to help design this FTAO wall. So again, segmented shear walls, that's the traditional method we're all probably used to. So I think we're 68% engineers on the line. So this method is really only using that full height wall segment, and it's ignoring anything that happens in between those full height wall segments. The hold downs for these are typically on each end of every wall segment. So you'll see here in this particular example, we've got 4 separate hold downs at the end of each wall segment. And that's to resist that overturning force and uplift. These can get eliminated in some cases if there's sufficient resisting dead load to counteract that overturning force, but that needs to get calculated by an engineer. Conversely, the perforated shear walls, which you should recall from Lori's earlier slides, are using that empirical adjustment factor that Lori pointed out, that C sub O factor, to account for the openings in the wall. Unlike the FTAO method, you're not going to see any straps around openings. Since this is an empirical method, it is limited to specifically tested conditions, and some imposed code restrictions make this tend to be less effective in design, because a lot of times you're not meeting all of those extra code restrictions. Hold down anchors for these, again, are only required at the very ends of the wall. So in this case, instead of 4 hold downs, we've only got 2 hold downs. But the anchors for perforated shear walls are going to be required to have to resist uplift at all of the full height piers. So that's kind of the trade-off. You're going to have potentially more robust sill anchors, but fewer hold downs. The height to width ratio that Lori was talking about earlier, and that is included in regular SPIDWIS limitations, that's that 3.5 to 1 for high aspect shear walls, and the 2 to 1 if you're not going to include any adjustment factor. For both the perforated shear wall and the segmented shear wall, that's going to use the full plate to plate height of your wall, and then the width of these full height piers. Force transfer around openings, or FTAO approach, is mentioned in the code, but SPIDWIS doesn't give specific direction for the analysis. It only references a rational analysis approach based on principles of mechanics. So in FTAO shear walls, the wood structural panels are going to transfer that shear around the opening. Anchor bolts are going to be used specifically to resist sliding forces, which is really equal to the applied shear force divided by the total length of the wall. And then the hold downs, which again are only located at each end of the wall, similar to the perforated method, those are going to resist that overturning force. And then the reinforcement around the openings can be a variety of things. I think the most typical type of reinforcing around the opening we see is strapping. So steel strapping around the openings. We're showing those here in black, but it can also be increased nailing and blocking around that opening to reinforce. So we've mentioned aspect ratio a couple times. Regardless of whether you're designing for wind and seismic, for wind load or for seismic, all shear walls that have an aspect ratio greater than 2 to 1, but less than 3.5 to 1, need to be reduced by an aspect ratio factor. Pre-2015, the reduction factor was 2 times the pier width divided by the height. Post-2015, it's been switched to this aspect ratio factor shown here. So 1.25 minus 0.125 times the height divided by the width. The designer does still have the option of using the previous adjustment factor. If you use that previous adjustment factor, which I think is usually a bit higher of a reduction, SPIDWIS section 4.3.5.5.1, exception number 1 says the designer does not have to ensure that the shear distribution to shear walls in a line provides the same deflection in each shear wall. So it is a requirement with the new adjustment factor. It's not a requirement if you use the old reduction factor. One of the major advantages of FTAO shear walls, or force transfer around opening shear walls, is that height to width aspect ratio is dependent on the height of the opening adjacent to the pier, and not the full plate to plate height of the pier. So this is allowing for reduced pier widths to meet that 2 to 1 or 3.5 to 1 aspect ratio. So this is a big advantage for designers who are dealing with larger windows. APA did a number of tests on FTAO walls several years ago, and you can download and review that research by searching force transfer or form M410 on APA's publication tab of its website. But this testing really led to 2 design resources that are also available for free on APA's website. And that's the APA technical note, which has a fully worked out example problem using force transfer on opening design method, and then the APA force transfer on opening calculator. That calculator is really an Excel-based tool for engineers to use for designing shear walls with multiple openings. And it's based on the Diekman design methodology. Diekman was a California engineer who developed this particular force transfer on opening design method. The calculator is based on US building codes and SPIDWIS, or Special Design Provisions for Wind and Seismic, which Lori talked about earlier. And this calculator gets updated annually, so it was just updated for this year. I've listed the calculator outputs here, which we're going to see on another slide coming up. But the calculator is set up for walls with up to 3 openings. Now, this calculator was created to design shear walls in a single story, whether that's 1 story in a 1-story building or 1 story in a multi-story building. And I'm pointing this out because once you start using the calculator, you'll notice pretty quickly that there's nowhere to input your dead loads or other vertical loads that might get transferred from levels above. And the calculator is really only going to look at load flow based on the lateral load applied at the top of the wall in that single story. So we're not putting in an option for cumulative loads that needs to get done post after you've used the calculator. To use the calculator, users enter the required information into the orange input cells indicated here by the red arrows. The applied lateral force is entered over here. This value should include all your required factors for load type. So whether it's wind or seismic, it needs to get factored before you input it here. And that's going to be either ASD or LRFD. The calculator is not going to apply any factors to whatever load you entered. So, so keep that in mind when you're using this tool. One limitation of the calculator is that it assumes that all of the openings have the same height. So if your shear wall has multiple openings of varying heights, you need to use the worst case scenario when inputting your opening dimensions. Regarding pier length or width, SPIDWIS 4.3.5.2, number 1 limits a pier length to a minimum of 24 inches. This tool will not limit you to 24 inches. This is based on APA study and laboratory testing of FTAO shear walls. And so the calculator will allow pier lengths a minimum of 18 inches long as the aspect ratio of the pier is 3.5 to 1 or less, and all the edges of the panel are blocked. An error message will appear if the pier length is less than 18 inches. Again, FTAO or force transfer on opening is based on rational analysis, so you need to use your engineering judgment. The FTAO calculator will also determine the shear wall deflection using both the 4-term equation from the IBC and the 3-term equation from SPIDWIS, that's Special Design Provisions for Wind and Seismic. The user enters project-specific parameters, including the unfactored lateral load at the top of the wall. This is sometimes also called V-induced instead of V-unfactored. We put V-unfactored in here just for clarity. We were getting a lot of questions about it. So this value should be the applied lateral force entered in the inputs section above, but without any load type or design method factors applied to it. The sheathing material, wood end post information and fastener information, as well as the hold down information that gets entered here, is completely separate from above. So please note the calculator is not going to internally verify that you've correctly designed your wall and that these inputs here are going to adequately meet the requirements in the design summary, that section above. The calculator's final design output is going to include a summary of the input parameters, the FTAO shear wall analysis with the full design equations shown, a summary of the final design requirements, and the total calculated deflection. These analysis results are going to fit on 3 pages, and they can get printed directly from Excel or saved as a PDF file to get included in your final calculation package. So either way, it's a pretty nice output. This tool was originally developed with seismic loads in mind, but APA has transitioned it over the last few years to make it more applicable in wind-governed areas. Most of the country is wind-governed, and you're dealing with much higher uplift loads, especially if you've got some large overhangs you're dealing with on your building. Now, in these wind-governed regions, shear walls can be designed to handle both lateral and vertical uplift loads simultaneously, but you're going to need to meet some basic requirements, and I've listed these out here. But we're kind of switching gears from that FTAO wall, and we're talking about combined shear and uplift now. So the last requirement on the previous slide was talking about that sill anchor spacing, and this is a really important part to get that uplift load and shear load into your foundation. And for this reason, there's a maximum anchor spacing. You can find this either in APA system report. This is Systems Report 101 if you want to search that for free download on APA's website, or in Table 4.4.1.6 in SPIDWIZ. This systems report is going to outline the basic design steps for making sure your wall can resist both horizontal shear and vertical uplift for wind at the same time. It also has several graphics explaining the minimum detailing, as well as an example. So I think today we've pretty much covered all of these things. Your shear wall and your shear wall sheathing is really doing for your building, and that's preventing that wall racking, adding stiffness to the building, transferring the lateral loads around openings where you're using the perforated method or the FTAO shear wall design method, and we're resisting lateral and uplift loads at the same time, potentially, if you're detailing it correctly. I think now we're gonna open it up for discussion.
Yeah, thank you, Alita. That was great. So actually we've had several questions. I think that we can start with you. First question was related to force transfer around openings. Can you design an FTAO shear wall with a door, or does it need to be sheathed on both sides of the opening? And I think, did your calculator have the capacity for that, or did you want to talk about that?
Yeah, we can absolutely talk about that. As I mentioned earlier, FTAO needs to be done using rational analysis. There are different methods of rational analysis. The calculator is really based on APA's FTAO testing that it did, which showed that the Diekman or Thompson method really provided the best results compared to the test data. And for the Diekman and Thompson methods, it's not really appropriate to use it with a door opening because there's no sheathing below the opening. It's really more for a window opening. And that's not to say that you cannot use FTAO with a door opening. It's just inappropriate to do it with the calculator because it's based on the Diekman method.
Excellent. I don't have anything to add. That was top notch. Thank you. Oh, here's a good one considering the picture you have on the screen right now. It's related to FTAO straps. And is there, some folks are asking if the straps are required to go the full length of the wall per SPIDWIZ. And that is something that we have tried to clarify in 2021, that the straps do not need to go the full length of the wall. What is required to go the full wall length, and sometimes even beyond that, would be the collectors. And that's, the collector that's transferring the force from the diaphragm to the wall. The straps simply need to be designed to transfer the force around the openings. So the requirement in SPIDWIZ isn't that it runs, the straps themselves run the entire wall length, although I think in this picture they do appear to. They're not required by code. It's based on a capacity requirement. So if the strap can transfer that force around the opening without going in the entire width of the wall, length of the wall, then it would not be required to do so.
And I think I'd just like to throw in there that sometimes there's a misunderstanding when we talk about collectors, because I know if you're designing FTAO, say using the drag strut method, a lot of people might consider the line above or below the opening as a drag strut. However, I think in SPIDWIZ, and you can correct me if I'm wrong, Lori, in SPIDWIZ, when they talk about that collector, they're talking about the collector at the very top of the wall. So it's either typically the top plates or the rim board that they're using as that collector, and not any internal wall elements.
Absolutely.
Yeah.
Oh man, all right. We've got questions coming in fast and furious.
I'm glad you're moderating it then.
All right. Question, does SPIDWIZ have values for staples? It does not. SPIDWIZ only has values for nailed assemblies. I believe there are values for staples in the IBC. Okay. Oh, okay, here is a question on the 3x SPIDWIZ requirement on 3x members at adjoining panel edges, and if that requirement applies at the sill. In general, it would not, because there are not panel edges that are adjoining at the sill plate, so that is something that when we say the 3x at adjoining panel edges, where you would only have one panel framing in from one side, that would not be considered an adjoining, pardon me, an adjoining panel edge. Okay. Question on, okay, it's not a shear wall question, but I'm going to take it because it is a SPIDWIZ question and it's a good question. Are there any exceptions on the 35-foot prescriptive limit for cantilever diaphragms? No, there are not. That's a prescriptive limit. So it's a hard limit at 35 feet. So if you wanted to design something beyond that, you would have to go outside of SPIDWIZ and engineer something through alternate methods. Here's a great question on nails. I am gonna take the screen back from just a moment to, I can get my PowerPoint slide where it needs to be. Okay, great. All right, so in table 4.3a and in the other shear wall capacity tables in SPIDWIZ, we do see the nail type and size is prescribed both by the length, the shank diameter, and the head diameter, and a minimum nail bearing length is prescribed as well. So that's the penetration into the framing member or blocking that would be required for a given nail. So there were questions on, can we use shorter nails that would meet that penetration and have the same diameter. In general, the tables are prescriptive, so you are not going to be permitted to change anything beyond what is prescribed. If you are trying to use different nails than are what is presented in the table, SpidWiz does give you an alternative option. It's ASTM D7989, which is a standard that allows you to determine the seismic equivalency to the system. So you would need to have a report from the manufacturer or third party that shows that these fasteners have been tested in accordance with that seismic equivalency standard. All right. Okay, here's one for you, Alita. For the FTAO calculator, if we're doing a wind design, should that be a ASD or a service level shear force that is used, or should the unfactored force be used?
Good question. So the unfactored force is really only going into that deflection section. Whether you're using wind or seismic or ASD or LRFD, just employ those factors when you're inputting it into the strength section at the beginning. So that first input slide where I showed the wall geometry inputs, and then they had the shear input on that in that section, that needs to be fully factored for your wind load. And then whatever you're inputting, so if that's an LRFD wind load you're inputting, the design requirements it's going to spit out in that design summary are going to be LRFD wind loads if that's what you input. So, so just keep that in mind. Definitely factor in the upper part, unfactored in the deflection section.
Awesome, thank you. Okay, here's a question on the 3x requirement for common framing members, whether or not that 980 PLF value was factored or not. That's a nominal unit shear capacity. So that would be the value that is in the SpidWiz tables, in table 4.3a or BC, whichever. So that would be the nominal value that you then would factor based on if you're using ASD or I'm sorry, you would adjust, not factor, you would adjust that nominal value based on if you're using ASD or LRFD. All right. Here's a good question. Are there height limits in SpidWiz for shear walls? We do not have height limits in SpidWiz. We do have aspect ratio limits, as I briefly alluded to and Alita talked about as well a little bit. There are height limits present in ASCE 716 for wood frame shear walls, wood frame bearing wall systems and building frame systems. If you look in ASCE 716 table 12.2-1, that's where they have different height limits for seismic systems. And you'll see in seismic design categories D, E, and F, there are height limits of 65 feet that would be prescribed for wood frame shear wall systems. And in lower seismic design categories, there's not a height limit based on that. It typically would come in from the building type or other elements, but short answer is no, SpidWiz does not have specific height requirements. Oh man, all right. This one might be good to have both of us chime in on, Alita. There's a question about garage door openings. So I know that there are many proprietary systems out there, and our different manufacturers of these systems have great resources online for using some of these proprietary systems around large openings in wood shear walls. And one of those common places where you see those used are in garage doors. But yeah, that is a question we get a lot. And
Lori, what was the question exactly?
It was just asking for some comments on garage door openings, because you do typically with garage doors, we do often see, a large opening surrounded by narrow piers. So
I'm gonna throw in here because typically when we're talking about garage openings or garage door openings, we're talking about residential structures.
Yes.
And when it does come to residential structures, if you're using the residential code, you can use a portal frame instead of a traditional shear wall, and that portal frame behaves differently than a shear wall. So a shear wall, essentially that segmented shear wall, usually when we talk about it, it's kind of analogous to a cantilevered beam that gets turned on its side, right? But a portal frame is really using frame action. And APA did do quite a bit of cyclic testing on portal frames several years back to help get it included in the residential code. We do have a technical topic on APA's website that talks about potentially including it in an engineered design. So it'll give you the allowable loads for those types of assemblies, but that's a site-built portal frame as opposed to a proprietary portal frame. So then it's not manufacturer specific.
Thank you.
That's a separate option.
Yeah, that had completely slipped my mind, and I appreciate you bringing that up because that is a very valid solution for a lot of designers designing, large openings around these garage door openings. Okay. And again, thank you everyone for submitting your questions. I have lots coming in still. There actually, thank you. I do have someone who reminded me there is a height limit on perforated shear walls that does limit those shear walls to 20 feet. So the height of the wall, that the individual perforated shear wall would be limited to 20 feet, but it does not limit the height of the structure that it could be used in. So you could have multiple perforated shear walls that could be used throughout the structure and have their hold down forces summed as necessary. Some additional questions on high aspect ratio walls and the reductions on the unit shear capacity. Alita, I think, did a good job covering some of the reductions that are necessary when we have aspect ratios in excess of 2 to 1. It's one of the comments that's in the SPIDWIS commentary that I like to bring up is that these high aspect ratio walls do have, again, that reduced unit shear capacity, but you do also need to pay attention to the loss of stiffness that can affect what is essentially the usable capacity of the high aspect ratio segments. So the high aspect ratio wall might reach its drift limit prior to developing that full shear capacity. So something that designers, excuse me, may want to be aware of, that just because the capacity of your high aspect ratio segment does calculate out and meet your strength requirements, you do want to be aware of the reduced stiffness. Okay. Here's a quick clarification. Alita, did you have the title available of that portal frame technical note?
Yeah, I'm sorry. I just looked it up. It's a
No worries.
TT100 portal frame with hold downs for engineered applications. So that's
Excellent.
TT100. If you search that on APA's website, you should be able to download it for free.
Great. Oh, here's an easy one. Where in the IBC is SPIDWIS referenced? That's in section 2305. So the 2021 IBC does reference the 2021 SPIDWIS. Okay, here, question on the shear walls in a line, which is in the 2021 SPIDWIS. This is 43551, I believe. So let me pull this up. We do have a requirement in SPIDWIS for shear walls in a line to have the same calculated deflection for each shear wall. And there were some exceptions. I think Alita addressed those, where we have the capacities adjust based on the 2B over H adjustment for wood structural panels, and then fiberboard shear walls have a similar adjustment. In these same sheathing provisions, we do, or I'm sorry, in these provisions, it does state that these shear walls have to be sheathed with the same materials. When we say the same materials, that's not to mean that they all need to have identical nail spacings and the same thickness, for example. This would just mean if we have a wood structural panel sheath shear wall and wood frame shear wall, all of those shear walls in that line would be required to have the same materials. So you could have a different thickness wood structural panel sheathing, or you could have a different nailing pattern, but that would still satisfy the intent of the code to have the same materials. Okay, here's a question. Alita, I know APA does this for diaphragms. Is there a recommendation for reduction of shear wall capacity based on overdriven fasteners? Do you guys have anything on that on shear walls? I recall seeing something, I think, that you all had put out on diaphragms.
We have done some testing on the effect of overdriven fasteners, and we have a tech note out on that. But essentially, fasteners in a shear wall, just like fasteners in a diaphragm, it's a very repetitive connection. So, if one or two are overdriven, it's not the end of the world. It's likely not going to impact the overall performance of your diaphragm or shear wall. It's really when you get some very significant overdriven fasteners, and it's a significant number of overdriven fasteners. So let me see if I can pull up that tech note. But typically, we say if it's overdriven more than 1/16 of an inch, and it no greater than 1/8 of an inch, and if it's under 20% of the nails or fasteners that are overdriven, then you don't necessarily need to reduce the shear capacity. It's really when you're over 20% of your nails are overdriven, then it's over 1/8 of an inch kind of overdriven. That's when you start needing to be concerned. And that's kind of spelled out in technical topic TT012, which is also available on APA's website.
TT012, you said?
Yes.
Great, thank you. All right, I think that is, we're getting close to the half hour here, so I think that's all we've got for today. I'll give it back to Marcy.
We just appreciate that you've been here with us today and hope that you found something of use. Have a great day.